Welcome back. So in this little series of videos, I'm going to look at self-attention and transformers. And these are models, or really layers within models, that have really basically transformed the whole fields of NLP and speech processing, and also increasingly computer vision. Let's start by talking about some of the issues that we have with recurrent neural networks. And I encourage you to go and watch the videos on recurrent neural networks and also encoder-decoder models before you plow into these videos on self-attention and transformers. So if we look at recurrent neural networks, such as this one, there are really two big issues that we can have. The one is architectural, and the other one is, you can think of that as a computational problem. So the architectural problem is really that even if we extend RNNs by using things like GRUs or LSTMs, even if we do that, we still end up with this problem that representations that are closer to the current observation has a larger influence on that hidden state than things that are far away. In other words, if we're looking at this hidden state here, it's almost inevitable that the hidden state that's closer to it here will have a larger effect on this hidden state than things that are really, really far away in the history of the RNN. And that's a problem, because if we have a sentence like Mr. Dursley of number 4 Privet Drive, located in a small town in Surrey, was eating his breakfast, then this word was is actually linked with Mr. Dursley. But because these hidden representations are so far away from this current hidden representation, it is just almost inevitable that these hidden representations with words that are close by will have a large effect on this hidden state. And that's the case even with the LSTM that has something like this cell state that gets propagated through over time. Because for Mr. Dursley to have an effect on this hidden state, you would have to make sure that you don't forget anything through this cell, this cell, this cell, this cell, and so on. And if this chain gets very, very long, it is unlikely that this cell would have a massive effect here. That can maybe be described as kind of an architectural issue. There's also a computational problem with RNNs. And that really comes down to the fact that to calculate any of my hidden states, I would have had to calculate the states coming before that one. And that means that I can't parallelize the operations. So if this was a feed-forward neural network, or even a convolutional neural network, then you would actually be able to calculate the hidden representations or the values of your kernels. You would be able to calculate that in parallel for this hidden representation and this one and this one and this one and this one, because they would only be based on what happened in the layer below it. But because we have an RNN, you have to go through this little for loop here in order to calculate the values of each of the hidden representations. So you can't just boom calculate all of these hidden representations in one parallelizable batch within an RNN. If you think about that in terms of what you want to do on a GPU, which really relies on several independent computations to be performed at once, then you can see that RNNs could be quite slow to train. And if you've actually tried to train RNNs, you would see that they're typically way slower than something like convolutional neural networks. So is there a way in which we can actually deal with this computational problem of having things that are far away also influence the current hidden state and also allow things to be calculated in parallel? Now, if you've gone through the previous videos on encoder-decoder models, you would have come across this idea of attention. And if you haven't done so, go back and watch the videos on attention. And it's interesting that if you just look at the attention computations, then they actually do solve these two problems that we have with RNNs. So this is an example from the encoder-decoder lecture, where you have an encoder RNN and then a decoder RNN doing something like machine translation. But I want you to kind of ignore just for the moment the RNN here and the RNN here and just focus on this attention part. So when we're calculating this y3 here, which is really a vector, how we're going to do that is we're going to take the dot product of this vector with each of the vectors in my encoder RNN. That's going to give me a bunch of values between infinity and minus infinity. I'm going to push them through a softmax so that I get these weights, they are all between 0 and 1, and they sum to 1. And then what I'm going to do is I'm going to multiply this vector with that weight and add that to this vector multiplied with that weight, and so on, to get this vector here. And that's then what I'm going to use upstream. Now the cool thing is, let's just for the moment pretend that these query vectors in my decoder and these values or keys from my encoder, let's just pretend that they've already been calculated and we have them. And then let's just focus on like the attention component here in the upper part of this diagram. Firstly, attention actually solves this problem that things that happened more recently has a larger influence on me. And how does this happen? So when I calculate this red vector here, which I then use at this third time step, this vector can actually weigh this very first word in my encoder. It can put a very, very large weight on that word. And so in a sense, attention allows you to look back right to the start of a sequence and weigh that very highly when I'm producing this third output vector. That would of course be based on the queries and the keys that I use, but you have an explicit mechanism that can look back and weigh things massively, even though they're very far away from the current hidden representation that I'm considering. The second thing is, if we go through this kind of hypothetical example where I tell you, listen, you've calculated all your keys and values and all your queries already, you have them in place. Then what you could do is actually calculate all of these vectors in parallel. Okay, so how would that work? Well, if I have my query here and I've got my values and keys here, then I can calculate everything I need for y1, while I'm also at the same time calculating everything for y2, because for y1 I'm just taking the dot product of this thing with each of the keys. For y2 I'm taking the dot product of this thing with all of my keys. And if we have these things, everything calculated already, then I can actually calculate the y1 attention and the y2 attention and the y3 attention in parallel. Of course, because I have recurrence here and I have recurrence here, I can't do that. But if we did have all our queries and keys and values calculated already, then I could actually calculate all of these things in parallel. And that's really the idea behind self-attention, which is really the fundamental building block of the transformer neural network. The idea here is that we're going to remove recurrence, and then we're going to rely solely on attention. Okay, so I'm just going to illustrate that intuitively, and then we're going to unpack that through this series of videos. So what does this mean? It means that when I'm looking at, let's just take this hidden representation here, what I'm going to do is, firstly, I'm not going to have recurrence between my hidden representations, so there's no errors here. And then what I'm going to do is I'm going to calculate this hidden representation as a weighted sum of everything in the layer below it. Okay, so I'm going to weigh that one. I'm going to add that to a weighted version of this one, and a weighted version of that one, and a weighted version of that one, and so on. Everything in the layer below it. So basically I'm going to apply attention over what happened in the layer below it and take a weighted sum of these vectors, and that's going to give me this current hidden representation. Similarly, for let's say this one here in the second position, I'm going to take a weighted sum of everything in the layer below it, and that's what's going to give me my hidden representation here. Okay, now what does this solve? Firstly, it means that if I'm calculating this hidden representation here, I can look back all the way to the start and in principle put a very large weight on that first word. So for this hidden representation here, which is kind of co-located with the word was, I could put large weights on Mr. Dursley, which is connected to this verb. So it solved that first problem that we have, kind of architectural problem. But it also solves our computational problem, because I'm going to structure this in a way so that each of these hidden representations, when I calculate their attention weights over the layer below it, can be done independently of the other hidden representations. In other words, when I'm calculating this hidden representation and I'm getting its attention weights, that's going to be independent of this one. And that means that I can run this thing on a GPU, and all these computations for all these hidden representations can be calculated in parallel. Okay, if we have a multi-layer self-attention network, so this would be one self-attention layer, we can have a second self-attention layer, and then again, this layer's computation is also going to be based on a weighted sum of the things that happened in the layer below it. So again, this one would be calculated as a weighted sum of the values in this layer, and for instance, this hidden cell would also be calculated as a weighted sum. And again, each of these we would be able to calculate in parallel on a GPU. And we're going to unpack the details of this, figuring out where the queries and the values and the keys come from for each of these self-attention layers. To really unpack that, we can look a little bit at the intuition from the Google AI blog post that talks about transformer neural networks. And I'll put a link to the notes here, and then you can just click on this link and that will take you to the Google AI blog post. And there they have this really, really nice diagram that steps you through what happens in the self-attention layers. So here, each of the hidden representations for each of those words would be calculated as the sum of the other hidden representations. And I don't want to go into the decoder, you don't have to worry about that. For now, we will talk about that later. So let's just look at that again. For each of the words, basically you have these like little weights going by, and these are, you can think of that as the attention weights. And for every position, your hidden representation is just based on a weighted sum of what happened in the layer below it. And that's kind of conveyed in this little movie from the Google AI blog post. So I hope that conveys some of the intuition behind self-attention and transformer models, and we're really going to unpack the details in the next few videos. The paper that introduced transformers and self-attention was called Attention is All You Need, and that's really just a snidey way of saying, listen, we don't need these recurrent connections between our hidden states within a particular layer in order to solve really complicated tasks. All we just need the attention from the layer that came before it.